Hello everyone, JCE Connect. In this particular lecture, I will be discussing about critical depth, critical velocity, minimum specific energy in terms of critical depth, and condition for maximum discharge. In previous lecture, we have been discussed about a specific energy curve, this curve. So we have discussed and we have seen how to draw the specific energy curve, and we have discussed various parameters, uh, then the types of flow based on the Froude number, that is critical, supercritical and subcritical, also mentioned in previous class. And here when we draw the specific energy curve, so it has a combination of two curves. One is E equal to y, another one is E equal to q square divided by 2gy square. So when you combine these two curves, we get the resultant curve, this one. This is the resultant curve, this one. So this is the resultant curve what we get. Then at one particular point, the curve gives a minimum specific energy. That point is marked as a C here. So corresponding to the point C, whatever the energy we get, that is a minimum specific energy, and corresponding to the minimum specific energy, whatever the depth we get, that is YC. That YC is called as a critical depth. Okay, so corresponding to the critical depth, whatever the velocity we get, that is a critical velocity. Then the minimum specific energy we get. So let us see in this particular lecture how the critical depth can be calculated, and what are the equation to be used to calculate the critical depth and critical velocity and specific energy. Okay, so here critical depth, first one is, I'll take it, critical depth. Critical depth, the depth of flow corresponding to minimum specific energy, is called as critical depth. And is denoted by YC. So in above figure, point C corresponds to the minimum specific energy, to the minimum specific energy, and corresponding depth of flow is the critical depth. So one can write the mathematical expression for the critical depth by differentiating the specific energy equation with respect to the depth of flow and is equating to 0. So how the critical depth equation can be formed? So first we should write the specific energy equation. We have a specific energy equation, that is E equal to y plus q square divided by 2g y square. This equation we are having with us. So for critical depth, we have to differentiate this equation with respect to y. dE by dy is equal to 0. So when you differentiate with respect to y, what we get this equation? So that is we get, that is d by dy of y plus q square divided by 2gy square is equal to 0. When you differentiate it with respect to y, the differentiation of y will be 1 plus, okay, then this is a constant, then differentiation of 1 by y square, you will get minus q square divided by you differentiate this one, you will get finally g, differentiate this one, you will get this equation. Then when you simplify this equation, it becomes y cube is equal to q square divided by g. Then y becomes q square by g cube root 1 by 3. Thus the critical depth, thus the critical depth is given as yc equal to q square divided by g whole raised to 1 by 3. This is the critical depth equation, yc equal to q square divided by g raised to 1 by 3, or else you can write yc equal to cube root of q square by g. This is the equation for critical depth. Similarly, critical velocity, what do you get? Critical velocity. Similarly, critical velocity vc. So these parameters are very important for the examination point of view. Many a times the derivation has been asked, so please practice these derivations. So here the critical velocity means the velocity of flow at the critical depth. The velocity of flow at the critical depth in this curve, the depth corresponding to the point C is called critical depth, and the velocity corresponding to the critical depth is called as critical velocity. It is velocity of flow the velocity of flow at the critical depth. At the critical depth is known as critical velocity, and is denoted as Vc. That is critical velocity. Then the mathematically how the equation can be obtained. Mathematically, we know that from above equation q square equal to g, that is gyc cube, from this equation. From this equation, q square equal to, we get gyc cube. Okay, but we know that q equal to what? Vc into yc. This we know already. Substitute the value of q here, we get vc square yc square is equal to gyc cube. Then from this we get vc equal to root of gyc. This is the equation for critical velocity. This is critical velocity. Critical velocity. Then condition for minimum specific energy. Next, third is condition for minimum specific energy. Condition for minimum specific energy. So for a given discharge, that is q, which is constant in a channel the specific energy is so we can get the specific energy as E equal to y plus q square divided by 2g y square. This is the equation we are having. And for minimum specific energy in terms of critical depth, if we want, then EC can be written as, in terms of critical depth, this is a critical energy, that is a specific energy. It can be written as YC plus q square divided by 2g yc square. But we have q square equal to gyq. So substitute in the above equation, we get EC equal to YC plus gyc cube divided by 2g yc square. Then when you solve this one, you will get EC equal to YC plus YC by 2. Then EC will be 3YC by 2. This is for minimum specific energy. This much is the minimum specific energy in terms of critical depth. I hope you understood this one. Okay. Then one more way of getting a minimum specific energy. Here we have a specific energy in other form, E equal to y plus we have v square by 2g. But q equal to what? A into v. So v equal to what? Q by a. When we substitute this one here, we get y plus q square divided by 2g a square. As seen from the specific energy curve, at point C, the specific energy is minimum. We have seen from this curve, in this curve, at point C, the specific energy is minimum. Corresponding to the minimum specific energy, whatever the depth we get, that is critical depth. And corresponding to the critical depth, whatever the velocity we get in a channel, that is called critical velocity. And this point refers to the uh, critical flow condition also. This point, critical flow condition, and the flow depth is called the critical depth. And then as a specific energy is a function of depth of flow. So from this curve we can conclude that specific energy, whatever we have been plotted here, it is a function of depth. As the depth varies, the specific energy varies in a channel. So we can write as specific energy E is a function of depth of flow. The function of depth of flow y. For minimum specific energy, dE by dy is equal to 0. So this is, here also we have solved the same. This specific energy is in terms of critical depth. This one is in terms of critical depth. Okay, so another condition we get as, when you substitute this one in equation, the same procedure to be followed, but what we get here, just differentiate this equation, then dE by dy, that is when you differentiate this equation with respect to y equal to 0, what we get here, dE by dy is equal to 1 plus, we get q square divided by 2g. Then again this area, area is a function of depth, then can be differentiated, minus 2 by a square into dA by dy, because area equal to what, b into y. So it's a function of depth only, area. So area have to be differentiated with respect to the y only, minus 2 by a square into dA by dy is equal to 0. So also we know that